Hi, my name is Rehana Mahfouz, and my project is about mitigating the effect of adversarial attacks on neural networks. Neural networks are vulnerable to adversarial attacks. There are two kinds of adversarial attacks on neural networks. Poisoning attacks corrupt the training data so that the classifier is not trained correctly. Evasion attacks corrupt the test data so that the output of the neural network just for that test data is incorrect, even if the classifier is trained correctly. Among the many types of evasion attacks, one type is gradient-based attacks. These attacks add some noise to the data, to the test data, and that noise is proportional to the sign of the gradient of the cost function. There are different ways in which this perturbation can be bounded. If the perturbation is L infinity bounded by a certain bound, let's call that epsilon, then that is called a fast gradient sign attack. If the bound is an L2 bound, that is called a fast gradient attack. There are different scenarios based on how much information the adversary has about the neural network classifier. If the adversary has access to the trained classifier and has knowledge of the defense strategy, that is called the white box scenario, which is actually really unrealistic because it is highly unlikely that the adversary will manage to gather so much information about the classifier. This is why I have not considered this scenario in my experiments. A slightly more realistic scenario is if the adversary has access to the trained classifier only, but does not know anything about the defense strategy. That is called a semi-white box attack, a semi-white box scenario. In both the semi-white box and white box scenarios, the adversary uses the original trained classifier to generate perturbations. But if the adversary does not have access to the original trained classifier, but only has access to the training data, that is called a black box scenario. In that case, the best that the adversary can do is try to guess the architecture of the classifier. So it trains its own model with the training data that it has and generates perturbations based on that. Procedure. This project is an attempt to devise a strategy to combat the effect of these adversarial attacks in the semi-white box and the black box scenarios. Since we do not know which bound the adversary will attack our data with, what kind of an attack they will use, we cannot just calculate the perturbation and then subtract it from the test data. Also, we need to find a strategy which would not hurt the classification accuracy if the data is not attacked. That leads me to think what I need to do to make the classifier learn the structure of the data, which would stay the same even if a small perturbation was added to it. The strategy that I came up with was to reduce the dimension of the data before passing it through the classifier. I do this dimensionality reduction using an autoencoder. An autoencoder is a neural network which tries to find an output which is approximately the same as the input. The hidden layer is of a different dimension than the input, which is why the autoencoder cannot simply copy the input to the output. If the hidden layer has lesser neurons than the input layer, then the autoencoder will be forced to learn a compressed representation of the data. The output of the hidden layer of a trained autoencoder gives us this compressed representation. My defense strategy involves first training an autoencoder with the training data. Then the compressed representation of the training data is obtained, which is used to train the classifier. An important point to note here is that the classifier architecture changes a little bit because the size of the input layer changes. So every time I want to use this defense with a different number of layers, I would have to train the original classifier again. Implementation details. I use the MNIST dataset, which consists of 60,000 training images and 10,000 testing images of 28 by 28 pixel, grayscale, handwritten digits. Each image is labeled by a digit between 0 and 9. The classifier I use is a fully connected classifier FC 100 the input layer has 784 pixels because the size of the image is 28 by 28, which means that there's 784 pixels corresponding to every image. So the size of the input layer is 784. That is followed by two layers of 100 neurons each, and the output layer has 10 neurons because one hot encoding is used. When the adversary does not know what the architecture of the original classifier is, in the black box case, it uses a different architecture. I made my adversary use FC 200, 200, 110. That is a fully connected neural network, which has 784 neurons in the input layer, followed by two layers of 200 neurons each, followed by a layer of 100 neurons each, and the output layer has 10 neurons because one hot encoding is used again. Uh, I chose a more complicated architecture for the adversary because I wanted to see how well my defense does against an attack that is crafted by a more complex architecture. I wanted to assume a worst case scenario. It cannot be the worst case, but a bad case scenario. The autoencoder that I use has an architecture of 784K 784, where K is the number of dimensions of the hidden layer. I consider K values of 330, 100, 80, 60, 40, and 20. For the fast gradient sign attack, I test my defense against attacks of epsilon values from 0 to zero point 0.5 with a step size of 0.05. The fast gradient attack is weaker and requires a larger bound to create a proportional effect, which is why I consider epsilon values from 0 to 2.5 with a step size of 0.25. The reason the bound of the perturbation is controlled is because the adversary wants the perturbations to be somewhat imperceptible so that the humans cannot actually perceive the perturbations. Results. It turns out that the dimensionality reduction technique using autoencoders significantly reduced the decrease in accuracy caused due to the adversarial perturbations. That is, it brought the accuracy up by quite a bit. I have plots for all the four cases, that is semi-white box fast gradient sign, semi-white box fast gradient, black box fast gradient sign, and black box fast gradient. In general, it turns out that the three dimensions that do the best are 60, 80, and 40. If I had to pick just one number of dimensions to reduce to, I would pick 80 because that seems to do the best. Discussion. In the past, principal components analysis has been used as a defense. The classifier is trained with the compressed representation that is found using PCA, and then the test data is projected onto the same subspace before being classified. I implemented this PCA defense to compare against my own defense. The performance of my defense is similar to that of PCA, which is not surprising because I only used a single hidden layer for my autoencoder. If I use deeper autoencoder architectures, it will probably create a better defense, and I plan to do that in the future. Something else that I noticed is that for the adversary to generate perturbations in the semi-white box scenario, it is very important for the adversary to have access to the trained classifier and not just know the classifier architecture. If the adversary trains its own classifier with the same architecture and generates perturbations based on that, the perturbations are not as strong. In fact, the perturbations are similar in strength to those in the black box scenario, where the adversary uses a completely different architecture to generate perturbations.